So the things that could improve is the stability of turning points. I just had a crash now. If you think about the turning point software, it is taking your clicks from your smartphone or computer, sending them to a server. I don't know where the server is. It's a small company, so probably they have it at home in their company in the US, and sends the click back via internet to my PC here. All of this starts in the wireless network of this room, crosses the ocean, comes back again on the same thing into my computer. And their software is not very stable. It's, perhaps they didn't take a course on socket programming or other reasons. If somebody is volunteered to do an interesting summer job, it's very easy from a networking viewpoint to send your clicks directly to my computer over the Wi-Fi of this room, or even better, over the Wi-Fi of my computer that I can set up in ad hoc mode. So we would have no competition, no traffic problem. There is a problem, which is to learn how to program in Visual Basic inside PowerPoint. I guess this is very far from trivial, but this is a small announcement. If somebody of you is interested in doing that as a paid summer job, come to me. We have an open position for that. And then if it crashes, we will have nobody to complain. But it will crash less because the software is complicated. As you know, if you have experienced large-scale software development, in general, large-scale software development does not work. It simply does not work, with a few exceptions. And those exceptions are called Google, Facebook, and things like that. But they have massive, massive resources. So the way to make things that work is to make them extremely simple, simpler than you would like it to be. And that's the philosophy of the internet. If you think about it, the internet has been designed with IP as the unique principle. It sends packets, and even though we spend an entire semester on it, it still is fairly simple. So that's really the key thing that makes it work, and is unfortunately not always adhered to in all the new developments, but is one of the founding principles. We'll see a few more principles when we come to the application layer in a minute. And now I'm finishing my intermezzo because I've found my slide back. We are studying BGP, and what we are interested in is how BGP interacts with the interior routing protocol and with the routing tables. Right? And this is a non-obvious issue because BGP is not done the way you would probably do it if you do a well-structured multi-layer system. In a well-structured multi-layer system, what probably you would do, you would have BGP computers, one per domain, that would talk to other BGP computers in other domain, and then would be like a super administrator of this domain that would speak to all the routers. This is how you build hierarchical things in principle. For some reasons, it's not at all the way it's done. As we have seen, BGP routers are simply a piece of software added to a router that does all the normal jobs of a router. So it's more at the same level as the ordinary routers, and that poses a number of issues on how to do the interaction. We have seen that the traditional form of doing the interaction, or not the traditional, but the simplest, intellectually simplest form of interaction is to do redistribution. BGP routers put into the interior routing protocol, into RIP or OSPF, all the routes they have learned from the outside as if they would be internal routes. And we have seen also that this does not work in practice because the interior routing protocols are simply flooded by the number of those routes, and they were not designed for that. With one exception, which is OSPF. OSPF has been designed for handling large number of routes. So redistribution is done with OSPF and practically never with any other routing protocol. Now, OSPF is not the number one protocol, interior routing protocol, so the number one method is not redistribution. I skipped a number of details on this. And then we have seen that instead of redistribution, we use injection. Injection means the BGP router that has learned for each prefixes that it has heard from the outside or from other BGP routers in its domain, it has learned the next hop, an IP address that is helpful in order to get to that destination, writes into the routing table, if it uses the injection method, the destination with next hop, which is in principle, which is illustrated here. We could have for a destination 10.1, the next hop is this, and this has been learned from BGP. This was a BGP, an IP address of an interface, probably between two networks, that has been learned from eBGP. And it puts that directly into the routing table, which in principle doesn't work, because in a routing table, the next hop has to be on link, and is usually associated with a MAC address if we want to cache the result of ARP, but certainly with a physical interface or a port number. In the case, if we do this, then we need to assume that we are able to manipulate, to handle such cases, which is classically called recursive table lookup, which means that if I have such a routing table, I have a packet to destination 10.1. something, then I will find this, which doesn't help because there's no interface. Then I will need to go back to the routing table to find how to go to this destination here. This is called recursive table lookup, and all commercial routers do this. Now we will see in detail how this can be done. Here is an example where we've done recursive table lookup. So R6 and R2 are running BGP. R6 has learned the prefix 18.1 with next hop 2222. So 18.1 is on the top, and 222 is the IP address of R5 on the shared network between R5 and R6, which, remember, the shared network is to be considered part of the interior routing of both networks. So we can inject this inside the middle domain, and we have 222 injected by R6. Similarly, R2 that speaks to R6 over IBGP will learn this and will inject it in R2. Now assume a data packet is received at this interface, the green here, to 18 something. Now I think we should say 111 instead of 123. Then R2 will do recursive table lookup. We'll find top 2222. Now 2222 is an internal address in this middle network, which means the interior routing protocol, RIP for example, will know how to write to 222. Therefore, the packet will be sent to the next hop, which is, for example, R1. Now comes the next question. What will happen at R1? So this packet arrives at this router here. What will happen? What do you think? I close in 5 seconds. And the correct answer is 3. It cannot be forwarded. So I'm happy once in a while I can catch you. If we do just what we said, we have 2 BGP routers, R2 and R6. Each of them can do injection, but R1 is not doing BGP. So R1 doesn't speak BGP, doesn't know anything about this prefix. So there is no injection at R1. Now, because we did not redistribute into the IGP, the route is present at R2 in the forwarding table, but is not redistributed into IGP, which means RIP will not propagate this. They are in a part of the routing table which is not accessible to RIP. If we do that, if we would like to RIP to propagate it, that means we would do redistribution into RIP. But we said we don't want to do this because it's harmful. There are too many entries. But then we have another problem. It doesn't work, simply. So the packet cannot be forwarded if we do only this. So if we do injection, we need to assume we do recursive table lookup, which is an easy thing to do. But we still have a problem. We need to fix the problem. How would you fix it? Remember, you want to do things as simple as possible. Anybody has a simple idea that would work? Yes? Default gateway at R1, that would not work because we're precisely in a case where we don't know whether the default should be here or there. Right? So default gateway works when you're a stub network, you're in the middle of, you're at the edge of the internet, and anything you don't know where to send, you send towards the core. But here, it peers with BGP to two sides. So some of the prefixes will need to go there, some there. So I showed a case where R1 needs to send to R6, but you could easily have the other way. No, we need to know which of the prefixes have to go left, which of the prefixes have to go right. So we need somehow to run a routing protocol for that. That's the goal of a routing protocol. Yes?
Add a header with destination R6?
We can add a header here. So like source routing header, for example, correct? So that's a good way to do it. We could say when this packet comes here, it goes to the routing table. Instead of just doing, it knows it's a border gateway, BGP. So instead of doing recursive table lookup, when it finds destination is 222, instead of doing the recursive table lookup, you could say, well, let me send the packet to this destination 222. There are several ways to do that. One way is to add a source routing header, which means the final destination is 18 dot something, but I add the source routing header. That means I should first reach that point, which is 222. That would work. That means the packet here would go via this to 222, but 222 is an internal address to this one, so the interior routing protocol knows how to go there. It would reach R6 or another point that goes to R5, and then R6 or R5 would remove the source routing header to do this. Another option is to do encapsulation. Instead of adding a source routing header, we could put the IP packet inside an IP packet that goes to 222. That's a good idea, but it's practically never done because source routing headers are practically not processed by routers because there are security problems. So although it exists in theory and is used in some very specific contexts, typically mobile ad hoc networks, but the core networks in the internet don't support source routing. So if you send a packet with a source routing extension, it will be simply ignored. For security reasons, that's a pity, but that's how things are. You've seen in the lab that routers do some minimal security checks. If you don't disable reverse path checking, a router does not accept a packet from an IP address on an interface which is not the direction to go to that interface, at least in some sense, which works only at the edge. We've seen that routing is asymmetric, but core routers tend to do other things. So they do verify whether IP addresses come and go in the correct directions. Source routing is, of course, an easy way to break those rules. If I am an attacker, I can use a source routing information to force the traffic to come to me or to a place where I will sniff the packet or forge them, for example. That's one of the reasons. Good or bad reason, it's not supported. Encapsulation is also typically not supported in backbone routers. Encapsulation makes makes virtual interfaces and tends to be disliked. Although we will see that when we do IPv4 with IPv6, we tend to do some encapsulation. So those two solutions are good solutions in theory. They are not done in practice. In practice, what people do is the simplest of all, which is run BGP in R1. So in this case, you will simply run BGP in R1. It's based on the principle of trying to make things as simple as possible. I mean, R2 and R6 are able to run BGP. So if R1 is a router of the same vendor, it's also able to run BGP. So why not run it? If we run BGP in R1, then R1 will receive the information from the BGP mesh. It will know that the next hop to 18.1 is 222, and then you will put it in the routing table. So why not? And this is, as far as I know, this is the most widespread solution. So that's the standard operation of BGP in operator networks. That explains why you will see BGP routers that are not connected to anything of the outside, which is a bit weird, but this is how. Now, of course, that poses a problem. That means if you are a backbone provider, you will probably run BGP in all routers. There are various tricks to avoid that. Typically, if your backbone is made in a way such that it has a very specific structure, you can avoid by using default routes, as you had suggested. You can avoid running BGP in some of the places, but in all the places that are in the mesh, in the core of your internet service, you will need to run BGP everywhere, which is not a problem for the routers themselves. The only problem is the BGP mesh. So BGP is based on the assumption that all BGP routers in the same domain can talk to each other. If you have a network like we have in the lab with 4 or 5 routers, it's okay. If you're a big operator with 100 routers, that means every BGP router needs to speak to 99 other routers, which perhaps is an overkill. So there are optimizations of this that we will speak a bit later that are called reflectors, confederations, among others. So the main benefit of this is that we separate completely the manipulation of the routing prefixes. The IGP, the interior domain, the routing method for the interior, needs only to discover all the topology of my network. So if there are changes somewhere in my network, the IGP needs to manipulate them. All the changes that are due to the outside world, they're manipulated by BGP, which has been optimized for that. So in some sense, we have the benefit of both systems. The other solutions you have proposed were encapsulation in some form or source routing header. We will see the last week a solution that is sometimes used, which is called MPLS. MPLS is one of those things I don't like virtual LANs. As you have noticed, perhaps, I think that the MAC layer is unnecessary. It's a legacy thing that comes from the past. In a pure IPv6 world, there's no reason for a MAC layer. I don't know when and if of my life on this earth I will see a pure IPv6 world, I doubt. So the MAC layer will continue, but the MAC layer is reproducing networking concepts that exist at the IP layer. But because it doesn't have all the flexibility that IP has, companies like Cisco have made a lot of complexification to the MAC layer. One of them is the virtual LANs that we have discussed. Another one is MPLS. MPLS is even worse than virtual LAN. It's making a large-scale network out of MAC layer by adding labels, like the virtual LAN labels, but labels that can be manipulated over long distance. We will see how this is done. This is with a concept called label switching. And with what this means in this network, if you would run MPLS, that means R2, R1, and R6 need to do 2 things, IP routing and MPLS switching. MPLS switching would mean when a packet comes here, like at R2 with destination 18 dot something, it would be tagged with a label, a bit like a virtual LAN label, that says, essentially the label says, go to next hop 2222. But instead of doing that as source routing or whatever, we associate a label to it. And then the internal things need to simply know how to go to that direction. Now there are issues, how do we map the label to the address 222, and how do we manage the labels? We will talk a bit about that a bit later. That's another option. That one works, unlike encapsulation and source routing, but it's based on the same idea. So this is, I guess, yes, so this is just showing that in practice we will run BGP internally if we don't use those other solutions. So that shows you BGP is fairly complex. Running BGP in a network is complex, like you will do in the lab tomorrow, because you need to translate policy into rules. That's a bit cumbersome thing. But also you have all those issues of knowing how you interplay with the routing table. How do you inject or redistribute, and how do you bootstrap the routes originally? So all of this you'll have to do, and in the lab we will do 2 or 3 methods that are commonly found. We will also now discuss a few other attributes. There are many, many attributes, one of the bad sides of BGP, but we'll discuss the most commonly used ones. The first one, all those attributes are used because it's a rule-based system. The decision process in a BGP router is based on rules, and in order to give more power to those rules, in order to supersede what the rules would normally do, then we add sorts of priority fields. So we can think of all those attributes as various kinds of priorities with different meanings tailored to different cases. A very common priority is local pref. Local pref is an attribute. It's a route attribute. That means when you look up a RIB, you have not only the destination, the network prefix, the AS path, the next hop, but also all the attributes. For example, a local pref. Local pref is a priority field that's assigned within a domain. So it's meant, in principle, not to propagate across domains. So you are not expected to see local pref attributes in an eBGP announcement, but in an iBGP announcement, you would see it. The simplest is to explain on an example. Assume here AS4 is connected to the internet by AS3 and AS2, but doesn't like going to AS2 for whatever reason. Perhaps because the link is very expensive or very high quality, but still wants to be connected, because connection in the internet, what you want to do before everything is to have reachability. You want to have robustness to your connection. So the internet is highly robust because there are lots and lots of connections between lots and lots of providers. But if you're connected to just one provider, perhaps you are susceptible to a single point of failure, which might be this link. So you want to mitigate this by being connected to several. With local pref, you can use this as a backup AS for you, for example. How would you do this? Then you would tag all the announcements that are received from, so R1, which is here. When R1 receives an announcement for AS2, it will tag it with a priority which is 50. So local pref, high means good. So when R1 receives it and tags to 50, it means it gives lower priority than a route that is received by R2. Now, if the internet works well, probably all prefixes that you hear over AS2, you also hear them over AS3. But they will have different AS paths, and they will have now different local pref. This one will put local pref 100, this one 50, and through the iBGP mesh, this will be propagated to each other. If we do this, what does R3 announce here? I close in 5 seconds. It's impossible, it's a bug. Because I had 29 responses, so it doesn't divide by 5. Well, the correct answer is, of course, the path through AS3, which is this one. Whoops. That's the correct answer. What will happen in this domain? R2 will receive 2 routes to that prefix. One, the one it has learned from eBGP, the one it has learned from R1. Then it will run the decision process, and then the local pref will come before. The local pref will have priority, so we will supersede all the other rules. The other rules is you prefer what you've learned from eGP for my BGP. So R2 will prefer that route. R1 will do the same, and R3 also. Both of those will, all routers will have the two routes in there. So those two will have the two routes. This one will learn the two also, and will prefer the route from AS3. And of course, one of the rules is we propagate only the route that we have preferred. So of course, the first route is not propagated, but is kept in the rib-in. So if, for example, this link breaks, this router will, if this link breaks, then all routers which have the other route through AS2 will now have it as the best and will propagate it. So that is a domain-wide preference that is, as you can imagine, very easy to use. Unfortunately, there are also other there is attributes. I say unfortunately because this is often used and misused. If you, the decision process tests a number of things. The local pref comes high in the criterion, but the very first criterion is the weight, which is a local priority that is only local to this BGP router. So it's not propagated to other BGP routers. So when one BGP router receives a route, you can have in the input processing rules a setting of a weight, which is a way to supersede entirely the decision process. That's why I say, unfortunately. If you are able to give priorities to diff by using a sophisticated algorithm that computes the weights for any incoming route, then you're able to do anything, any choice, not just follow the decision process. I say unfortunately because there is still the decision process, so there's an interference between the logic of how you set up the weight and how the decision process works. But you will be able to experience that in the lab. A more classical, or weight is very classical, but a more, I would say, a cleaner attribute is the MED, MultiExit Discriminator, which is used in this case. Remember, we have seen this case already where we have one AS that has two prefixes, 10.1, 10.2, and then depending on how we originate the prefixes in BGP, we could have, for example, that R3 originates 10.1, R4 originates 10.2, and that's all. Or we could have that both R3 and R4 originate both. And of course, the second is more robust. The first one makes more sense. You say you originate the things that are local to you. But if the BGP process in R3 crashes, for example, then we have lost reachability for this prefix, which might be bad because perhaps we have crashed the router or just the process, but it's still reachable because this domain may have, usually has internal paths. So it's possible to go from here to here. So if this announcement or this BGP connection doesn't work anymore, we should be able to use the other path to reach that here. Nonetheless, we have seen that if we announce both together, then we force all traffic to go in a certain way. If we want to change this rule, we can add this type of priority, which is now small means better. So here, the idea is that this router would announce the two prefixes, 10.1 and 10.2, but will give a MED field that is better for 10.1, which is 10, and for 10, and here the reverse. And the idea is that the routers in the other domains that receive this information, they know that both 10.1 and 10.2 are reachable, that both are reachable from those two routers, but the semantic is we prefer you to use this router for 10.1, i.e. this link for 10.1, and that link for 10.2. So we would like that ASX routes traffic to 10.2 through ASX and not through me, right? Which is typically what we do if Y is a customer of X, right? If you're a customer, you're connected to Swisscom at different points, you still have internal links, but you would like, since you receive your service from Swisscom, you would like to use Swisscom service as much as possible, or perhaps the other way around. But if that's what you want, you will use the MEDs in this way. for example, here, what will the decision process at R1 do? I close in 5 seconds. Oh, no, it's a close tie. So we are in R1 and we're discussing the routes to 10.2. It has received one from R2 via the iBGP mesh, one from R3, and it applies the decision process. So let's go to the decision process to test what this will be. Here's the decision process. We test those in order. We've seen local pref, that doesn't apply here. Shortest AS path and lowest med. So it will find what is the shortest AS path to the destination, to the next hop. Where is my slide? 59. So the shortest AS path to the next hop, so it has 222. Well, that's weird. It has 222, and so the next hop to this one or that one. Thank you. So if it picks the shortest AS path, I guess it would pick this one here, which is the route via R3, which is what the majority said. To be honest, I'm surprised. I was expecting the other way around, but this is what the decision process says. So the decision process here will pick the shortest route and will only make sure you find the desired thing if the distances to the interior distances are equal, which is not the case here. Well, that's how it is. Okay, we do a break and we resume and rediscuss that perhaps in 14 minutes. So I owe you an apology. I think the correct answer was the majority, as not always in Switzerland. So the decision process will test a number of things that we have seen. It will test the AS path, and I was confused by the number of... The AS paths are the same here for those two announcements, the one received from R3, the one received indirectly from R4. They have the same AS path. So the next priority field that is discriminating is the med. And the med, for some reason, lower means better. So this router will prefer the route with med equal 10, which is this one. That means it will route to 222, so via R2 here. So the traffic will go this. Oh no, so that is correct. So it's via R2. Sorry, it will route via R2, which is here. So let's write the correct answer. The route via so as two routes to 10.2, let me see, yeah, 10.2, it will prefer the one with the smallest med, which is that one, R2 here, which is the traffic will go this way, which is the intention of the med. The intention of the med is for this network to say to this other one, which is presumably a service provider to this one, traffic that goes here, I would like to commit here. Because if it goes via this, I will need to transport it internally. Right? So this is what will happen. So let me skip a few of those, which are easy to see. I will skip also the community export. There are, as I mentioned, a number of bells and whistles in BGP. One of them is important, is the fact that BGP does only deltas. The BGP propagates only changes to the routing information, which is nice most of the time, because that means most of the BGP traffic is small. Even if you have 500,000 routes, presumably the topology of the internet doesn't change a lot. But in the past, there were still issues, there were problems that were caused by routers that crashed and rebooted, or a routing process, BGPD, crashes. Then you have a smart machine that detects it has crashed and reboots. And then the fault was not cured, so the fault condition comes again, it crashes again, etc. What happens in a BGP network if that happens? When a BGP router crashes, all the neighbors that had received announcements for this one will detect it with a keep alive. They will decide that all those routes are invalid, so they will mark them as invalid in their RIB-in. They will reapply the decision process, and this change might propagate through the entire network, as we have seen in other cases. Now, if a minute later the router comes up again, then there will be again an activity in the network, and that will keep going on forever. So you will have BGP routers that are always computing new routes, and while they are computing routes, of course, we have transients. We have some part of the network that have the old values, some that have computed the new, so we might have routing loops, we might have a number of bad things that happens, as usual, with transient in routing protocols. So this has happened. This has happened really in the past. So a fix came, which is called route flap dampening. So the solution is the following. When a route is withdrawn, remember, a BGP announcement can be an update or a withdrawal. Withdrawal means I receive a message from a neighboring router, withdraw it. Or I can detect that this router is dead and this router decides to withdraw it, or I receive the information propagated through other BGP routers. Then when I withdraw it, I don't delete the route, I keep it, and I mark, of course, a flag saying this is invalid. This is the same as we do when we use Git or SVN to do software. When we do something new, we don't delete the old thing, we create a new version. That's a good idea for anything we do. So we do the same thing here, and the router is kept, and it has an attribute which is a penalty. When the route, if there is this problem, the route will come up very soon. So when it comes up very soon, then we will update the penalty field that was remembered here from the previous thing. And if the penalty field is too high, we don't select this route. The penalty field is illustrated on this diagram. So this the penalty associated with a route. Whenever this route is coming up again, we add a penalty. If it's considered deleted, we don't care about the penalty. The route will not be used. But when it's added, we activate it. But before activating, we compute its penalty. And if the penalty is too large, which will occur if the route is reactivated many times in a short amount of time, then the penalty will be too large. When it goes above some level, then the route is not used. So it still exists here. It is in the RIB-in, but it's considered as an invalid route that we should not use, as if it had been withdrawn. If the flapping stops, if the router that was the cause of the problem is killed or fixed, then this will not happen. For example, if a route has been reestablished many, many times, the last time is reestablished, it will not be used, but the penalty decays exponentially with time through various possible mechanisms. And when the penalty becomes small enough, the route will be considered valid again and will be reestablished. So it's what we do with nasty people. If you do bad things again and again, then you're considered a bad person. And if you ask again your friend to lend you your iPhone, but whenever you lend it, you don't give it back or whatever, then after a number of times you've done it, then you're not considered a valid friend and you don't get a service, right? But if you behave well over a long period of time, people forget. So this is a classical forgetting thing we use in machine learning for adapting those kind of things. Another bell and whistle that has been done is not surprising for us. We've seen that for IP addresses. AS numbers are not IP addresses, but like IP addresses, there are private AS numbers. So there are AS numbers that are in principle not to be used in the global internet. Now, BGP is used only in the global internet, so in principle, they are never used. They can be used for testing. If you do a lab, for example, you can use AS numbers, and you can be sure that it will never, even if it leaks to the outside, you will not hurt. Or it is used in another context here by clients that don't have an AS number but still want to use BGP. Looks a bit crazy, but it is possible. If you are, for example, a client to a provider, like EPFL is from Switch, you in principle don't need an AS number. We have seen you can use default routes. But if your topology is a bit complicated, you might still want to use the full flexibility of BGP to pass the or if you have a lot of prefixes that are not contiguous, if you have, I don't know, 2,000 different blocks of prefixes, and those things change because the lifetime of a company between fusions or acquisitions or destruction is about 2 years. So companies always change something. They find a new office, buy a startup, or they're broken into pieces. So the prefixes that exist in a company, they change, not every day, but certainly they don't stay constant for months or years. So if you use default routes, you need to inform the default routes, you need to inform the higher layer of all the prefixes that are done here with mechanisms other than BGP. So in cases like this, you will still want to use BGP, but you don't want to have a BGP number because BGP numbers are not many and we want to use as few as possible. In a case like this, then we use a private BGP number, a private AS number that will, an AS number is needed to run BGP, but whenever provider receives a route from client, it will replace the AS number of the client by his own AS number, so that it will not be visible in the rest of the world. And this works because this client is client to only one ISP. Otherwise, this scheme doesn't work. If you're client to several ISPs, you need your own public BGP number. But because this client is client to only one ISP, all traffic to and from this client always goes via this ISP. So will always be routed to this ISP number first. That's one use of private numbers. Now, if you have private numbers, you could have a case like when client sent a BGP announcement, the route that was received, when it's received by the provider, will add the private AS number of the client. Then when we forward an announcement to an outside provider, to an outside BGP peer, we have our own, I am now the provider, I have my own AS number, plus I have to replace the AS number of my client. So the same AS number might appear twice in the path. This is legitimate. It can happen that an AS number appears several times in a path. It's not a bug. BGP will not treat that as a bug or an error. It can be used to detect loops, but if you have a block of contiguous, in principle, you assume it's not a loop, but it's something else. This principle can even be used and abused. Assume, for example, this BGP system is configured to use things like AS path for 2.1 equal to 100 and to 2.116 when issued by R3 with a larger AS path, which is 4 times repeated the same AS number. Assume we do this. We have programmed this BGP router to do it in this way. What will happen now if I am a packet issued by Z that wants to go to this prefix here? Which way will it go? I close in 5 seconds. And the correct answer is the majority vote via Y. Why is that so? Well, here it's simply because the routers in Z will apply the, now, of course, I'm assuming there are no other hidden priority fields like local pref or wait that is added by routers in Z. But if nothing else is done, they will prefer the routes that have the shortest AS path. Now, those paths are longer because we have artificially inflated the length by repeating the AS number. So those paths are shorter. So it's a way to signal to the rest of the world that I prefer to go this way than that way. Why don't, which is the same purpose of multi-exit discriminator, MED. So we could have used MED instead, but in practice it's not done because MED is in principle not used MED is used only in a client, in a customer-provider relationship. So this guy can send a MED to this one if this guy has two access points to X here. But X will not forward to Z the information about MED that was sent here. The semantic of MED is, it is about the relationship between a customer and a provider. So those guys, the Z will not know that client prefers traffic to this, to go this way than that. It will not know it via MED. So this trick is used and is considered a legitimate trick. So you see that there are, when you try to play with when there's an art which is of being a BGP expert. So with what we've seen, you know BGP. If you're really serious and want to make a living out of working with BGP, then you will need to do an internship at a provider that runs BGP and learn all the tricks that are used to obtain what we want from the route. In the past, we did a lab that was longer, but the student feedback is that it's too long, so we've reduced it. We can easily create collections of rules that are inconsistent. So BGP is not bulletproof. A collection of providers may come with decisions. Typically, A prefers to route via B, B prefers to route via C, and C prefers to route via A. If that happens, it should not happen in principle, according to the rules of transitivity, of friendship, and things like this. But in practice, it's not as simple. So that can happen. If that happens, you have routing loops. So the BGP announcement will not converge, and you will have a perpetual transient, and the routing will have problems. So the best thing to do is to screen your rules very carefully and be sure it doesn't happen. We have mentioned the problem of the iBGP mesh. BGP requires all routers to connect to all. In large networks, this is considered a problem, and so there is a solution. The simplest solution is to combine all the elements we've seen together, is to treat a large domain as a collection of several smaller domains, run BGP inside this large collection of domain, and it's called a configuration, by giving private AS numbers inside the domain here. So here I'm showing a domain with 3 subdomains that has 3 private numbers, P1, P2, P3, and then you run this collection as a simple part of the internet, which means there will be a full mesh inside each of the subdomains, but between the subdomains we will run eBGP, which is run internally, but it's still the eBGP. It will follow all the rules of eBGP. And in this specific example, which is too simple to be interesting, there are single points of failure. If we lose the connection between the top routers here, of course, the domain is disconnected. So in practice, you would probably run several eBGP connections between the subdomains, but we reduce the problem of the mesh here. Of course, we need to configure a substitution of the AS path. When we export here, in the export rule, we need to specify what we do with the AS path, whether we substitute P1, P2, P3 by Z, and whether we substitute every instance of P1, P2, P3 by Z, or whether we substitute any path that contains P1, P2, P3 by a single Z. Those are the kind of things that needs to be specified. For some reasons, this solution that seems intellectually the most appealing is not the only one that exists, although this one is deployed, but some people have deployed other ones. They have deployed an ad hoc mechanism inside BGP to avoid the mesh, which is functionally the same as doing a confederation, but does not require manipulation of the AS domains. It's called route reflectors. So the idea here is that you have you divide your domain into subdomains that are called clusters instead of subdomains. And within one cluster, you have one or two route reflectors that act as a repository for all the internal BGP information. So a route reflector will re-advertise all the routes it has learned inside this IBGP mesh. It will advertise it to all the other IBGP route reflectors. Functionally, it's exactly the same as the confederation, but the names are different. Why the two exist, this is not clear. But as I understand, this is used more than confederations. In some cases, you even have an eBGP mesh. Can you imagine where and why that would occur? When Swisscom peers with, I don't know, Sunrise, for example, what they can do is to agree on a link between the two, a fiber, and then they need to share the cost of this because this link is now belonging to the two networks, put a BGP router at each end. That's one way of doing things. There's another way of peering between networks, which is to use one of the peering points. So peering points are companies that offer a service of interconnecting many networks together. So instead of agreeing with my competitors on the list line, I can simply come to a peering point, put my BGP router, and then I will connect to all my competitors who are in the same peering point. If I have one or two competitors that I connect to, probably I don't want to do that. If I have 100, then probably I will do that. So historically, there are two very big peering points that are called May East and May West. You might have heard of. They are, in fact, they are in the US, one on the East Coast, one in the West Coast. And those are places where all US providers interconnect. Those are typically rooms, a bit like the Internet Engineering Workshop, full of computers in a basement of a building because it's cool, naturally cool. You reduce the cooling expenses. And they are the fragile points of the Internet. If you destroy one of those peering points, then you've destroyed a lot of connectivity at the BGP level. Now, inside the peering points, in large countries, you may have hundreds of thousands of interconnections. So you have you have what you call a BGP mesh inside a peering point. So you also have what is called a route server, which is a bit similar to the route reflectors that were used inside an IBGP mesh. You can have one, if you're offering a service of a peering point, you can offer also a route reflector service where instead of having one BGP router connect to all the 999 other BGP routers of that peering point, I connect only to the route reflector. So this is also what is typically done. And those route reflectors are typically also exporting everything they see to the internet so that you can see from those route reflectors all the BGP announcements that are done by various companies here. Voilà, that's the reality of BGP, which is in some sense the reality of the internet today. BGP is the core protocol that runs the internet. How is BGP in Switzerland? Well, here are a few examples. So we have here a number of internet service providers that connect, for example, to Switch. So this is the Switch view of the internet. So Switch peers with all those providers at a peering point at CERN, at the peering point in Basel, another one in Zurich, and another one in I guess Lugano here. I think there is one on the Bodensee in the Lake of Constance. This is an example of a Swiss peering point, Swiss IX, at least when I collected the slide a few months ago. I think the name has changed in between. So if you want to open an internet service, all you need is to connect to one or two of the Swiss peering points. And you can find that, you will see that the costs are not so expensive. This is if you go to the Aroute reflector, for example, you can find all the information about Switch. Switch is our provider. The AS number is this one, and a bit like DNS, you can find also information about all the BGP relative status. Seen from EPFL, here is the interconnection. So it's not really seen from EPFL because EPFL from the world is inside Switch. When we send an AS path that goes to EPFL, it switch. So this is a 559, which is, again, has nothing to do with an IP address. It's just the AS number of Switch. So Switch is connected to all those different other internet providers that themselves are connected to others, etc. So you can build a graph of the internet seen from EPFL. Now you can and you can see this is saying what kind of peering agreement there is between Switch and others. You see that Switch is a client to two networks that are providing probably access to the US or to other places, and is a peer to a large number of other internet service providers. Some statistics about the number of prefixes. I said 500,000. That's true for the number of AS prefixes that are announced by a BGP router. Each of them will be placed in the forwarding table, right? So 500,000 is the number we have. This is IPv4 prefixes. And this is the number of ASs that exist in the world. So we're close to 50,000 ASs. The number of prefixes announced for IPv6 are much less, 200,000 versus 500,000, much more than was hoped. So when IPv6 was designed, the idea is that we could do a lot more aggregation, so we would have much less. We don't, because as you know, IPv6 still is a toy. Most traffic is on IPv4. So now the end of this is that we have all the IPv4 prefixes plus the IPv6 prefixes. So in total, we're closer to 1 million prefixes than to 500,000, which means that there's a lot of work for BGP routers to carry all this information. Voila, that's all for BGP, at least for the theory. The next step is to look at how it works in reality and in practice.